Okay, so what we got here is a problem that we did for your homework. In order to solve this problem, we used the equation of motion because up until that point we hadn't learned how to use the momentum and impulse equation to our benefit. But now that we've learned that, we can take another look at this problem and see how using the linear impulse momentum equation that we developed in class can actually help us solve for this desired quantity in this problem a lot faster than how we had to solve it in the homework using the equation of motion. So here we have the crate has a mass of 150 kilograms. It rests on a surface for which the coefficients of static and kinetic friction are mu s is equal to 0.3, mu k is 0.2. If the motor M supplies a cable force, that's a function of time, 8t squared plus 20, which is in newtons. We want to determine the power output developed by the motor when time is equal to 5 seconds. So as always, we're going to start writing down what is provided in the problem. So among those things is the mass of the crate is 150 kilograms. We know the static friction coefficient is 0.3. The kinetic coefficient is 0.2. The kinetic coefficient is generally less than the static friction coefficient. Once we get an object moving, it doesn't take much force to keep it moving. So the force that's generated by the motor on the cable itself is a function of time, 8t squared plus 20. This is in newtons, where if we insert time in seconds. And what we're looking for here is the power that's required by the power out from the motor, we'll say, at a moment in time, time is equal to 5 seconds. Okay, so let's visualize what's going on in this problem. We have a crate, of course, that's attached through this pulley system to a cable that is being drawn in by the motor itself. And the force applied to the cable from the motor, as we said, is a function of time, 8t squared plus 20. So initially, okay, at time is equal to 0, if we plug in time is equal to 0 into our force equation, then we find out that at time is equal to 0 seconds, that the force initially is 20 newtons. Okay? At a later time, when time is equal to 5 seconds, that force that's applied to the cable itself would be equal to 8 times 5 squared plus 20. So that'd be 5 squared, 25. 25 times 8 is 200 plus 20, so that would be 220 newtons. Now this is the force that is applied to the cable itself from the motor itself. Okay, if we were to draw a free body diagram of the crate, what would it look like? Well, here's our crate. We know that it has a weight force downwards. They give us the mass, so the weight would be equal to the mass times the acceleration due to gravity on the surface of Earth. The normal force would counteract that, pointing directly upwards. The cable force is pointing to the left, and this force, for a third time, is a function of time, 8t squared plus 20. We also recognize that by looking at this setup here, that the crate is actually attached to the cable in 3 different locations. So 3 times that cable force is pointing towards the left, right? Because if we were to take a section of the rope, if we were to fictitiously cut this rope, in our minds we know that there's a tension force there, a tension force here, and a tension force down there. All 3 of those combined work together to pull the crate towards the left. So there's actually 3 times that force, that time dependent force pointing towards the left, pulling on the crate itself. And then pulling to the right, we have our friction force, which initially is going to be mu s times n, but once the crate starts moving, if the crate even starts moving, that will switch over to mu k times n. Okay, so when it comes to friction, we have 2 different types of friction. We have static and we have dynamic. For static friction, the static friction force is always going to be less than or equal to mu s times n. This equal to sign here indicates the maximum threshold that the static friction can withstand. Okay, it's the maximum that the static friction can be. So if we were to call Fs max, this would correspond to exactly when us is equal, or when the static friction force, the maximum, is mu s times n. When the static friction force is exactly equal to mu s times n, it has reached its maximum threshold. Any additional force beyond that, the crate cannot withstand that. The static friction force cannot withstand it, meaning the crate will start moving to the left. Okay? So this will correspond to, in this case, 0.3 times the normal force. How do we determine the normal force? Summing the forces in the y direction equal to 0. There's no acceleration ever upwards or downwards in this case. Even once the crate starts moving, it'll just be moving to the left, so it's never any acceleration in the vertical direction, upwards and downwards, meaning the weight minus, or actually minus weight plus the normal force is equal to 0. The weight force is equal to the normal force. Therefore, the normal force is equal to the mass times the acceleration due to gravity. Plugging this new relation for the normal force in down here, we find that the maximum friction force, static friction force, is going to be equal to 0.3 times 150 kilograms times 9.81 meters per second squared. I use the units in my equations to remind myself that I'm dealing with SI, not English engineering units. So 0.3 times 9.81 times 150, I get 441.45 newtons. Okay? This is the maximum that our static friction force can be. Our static friction force cannot be any larger than 441.45 newtons. That means if I were to pull to the left or to the right, doesn't really matter, but if I were to pull in one direction with a force that's greater than 441.45 newtons, the object will start to move in that direction, and the friction force will become a kinetic friction force, which depends on the coefficient of kinetic friction, that 0.2 value that we've included before. So the maximum value that the static friction force can be, I'll write down max here to remind ourselves, is 441.45 newtons. Okay, this force that we're pulling to the left, according to our free body diagram, is a function of time. It's 8t squared plus 20 times 3 times that force. So the first question we want to ask ourselves is, at what moment in time will this pulling force from the motor surpass this maximum static friction force? At that moment in time, any additional force beyond that will cause the crate to start moving to the left. So the first thing we need to solve for is, at what time does the pulling force surpass the maximum static friction force? So this happens when the 3 times our pulling force, t squared plus 20, becomes exactly equal to our static friction force, which we said was 441.45 newtons. Okay, so we have a force pointing towards the left, and we have a force that's pointing towards the right. Force to the left is our pulling force, the force to the right is our friction force. Turns out when we solve this equation, time is equal to 3.987 seconds. I carry around a couple significant figures here so that by the end I can decide to eliminate a number of significant figures with my final calculation. So I carry around several significant figures at this point. Okay. So the way you would have solved this problem in the homework was then to set up your equation of motion, the sum of forces in a particular direction is equal to the mass times acceleration in that particular direction. Then we would have had to solve the equation in terms of acceleration, integrate it in terms of time, from some initial time to a final time, and so forth. But what I'm about to show you is, once you've gotten to this point, we can use our linear impulse and momentum equation to solve this a lot faster. Linear impulse momentum equation says that in a particular direction, the mass times the speed in that direction, I'll call it the x direction, plus the sum of all external impulses from some initial time to some final time, this is force dt in that direction, is equal to the mass times velocity at some later point. So I have to put subscript 2 and subscript 1 at the proper locations. This is our linear impulse momentum equation. And if we say that the x direction, it doesn't matter what direction we call positive, but for the purpose of this equation, let's call x positive to the left to make our lives a little bit easier. We know that the object, the crate in this example, is actually going to be moving towards the left. Well, taking a look at this equation says that, well, at some initial time, the object that you're considering is going to have some momentum. Okay. Then the second term says that with that initial condition, you're going to add to it some amount of impulses, which is the product of force and time. And after you perform all of those impulses, the object will have some new momentum, mvx2. What we recognize is that initially, this crate is not moving. So that first term goes to 0. It has 0 momentum. Okay? So if that first term goes to 0, then we have to focus our attention on this impulse term, which is considering all the forces that exist in this x direction and integrating all those forces over the suitable period of time. So if we go back to our free body diagram, we recognize that in the x direction we have two forces. We have one force that's pointing towards the left, 3 times F, where F is this time-varying force from the motor. And we also have a force that's pointing towards the right, that's the friction force. But of course, once the object starts moving, that friction force is going to be the product of mu k times n. Once the object starts moving, we have kinetic friction at that point. So if we say positive to the left for the purposes of this particular equation that we're using, then we can set up this equation by saying the sum of impulses from an initial time, 3.987 seconds, this is when the object starts to move, to some final time, well, I'm going to put 5 seconds here because this is the period, the moment in time that we're solving for our final speed, is equal to, or the integral of our force equation, so 3 times 8t squared plus 20. This would be in our positive direction, so there's a positive sign in front, minus the impulses in the opposite direction, the forces that are acting towards the right in this equation. So this would be 0.2 times the normal force, 150 kilograms, times 9.81 meters per second squared, dt is equal to the mass of the object times its final speed in the x direction. Notice that I had to be careful with my signs. This first term in the integral is the impulse, is the force that's pointing towards the left. This is the force from the motor itself that's pulling on the cable itself. We have 3 times that force pointing towards the left. This is a positive impulse based off of our definition of the positive direction for the linear impulse momentum equation. The second term here is a negative impulse because the friction force is pointing towards the right, which is in the negative direction based off of what we called positive x for this particular equation that we're using. And then we have mass times velocity. This is the final momentum after all of these impulses have acted on the body itself. We would expect Vx2 to be a positive value because we expect the crate to be moving towards the left after this is all said and done. So when we evaluate this integral, 24t cubed over 3 plus 20t minus 0.2, 150 kilograms times 9.81 meters per second squared times t. You evaluate this integral from 5 and from 3.987, these are in seconds, This is going to be equal to the mass, 150 kilogram times its final speed. Okay? This problem was asking us to solve for the power out from the motor itself. Okay? And we know that the power is going to be the force dotted with the velocity of the rope coming towards the object at that given moment. So once we determine what Vx2 is from this equation, that tells us the speed at which the crate is moving towards the left. But that's not what the question is asking us for. When we solve that equation up there, by the way, Vx2 is equal to 1.704 meters per second. This will be a positive value, meaning that the speed of the crate at 5 seconds is 1.704 meters per second to the left. If we want to know the power out from our motor, we need to know the force that's supplied by the motor at a time of 5 seconds. And we need to know the speed at which the rope is entering into the motor, the speed at which it's pulling the rope in towards itself. What we solved for here was the speed of the crate, not the speed of the rope. So the last thing we need to determine is the force on the rope itself, the cable itself. We solved for that previously, the force on the rope at 5 seconds. That was one of the first things we did. We said it was 220 newtons. So at 5 seconds, the motor is pulling in the rope at 220 newtons, and the speed at which it's pulling in the rope, well, in order to determine that, we need to use our dependent motion analysis. I'm going to have one datum, and I'm going to have one position vector that points to the right, call this S sub A, doesn't really matter, and then I'm going to have another position vector that points from the datum to some fixed location on the rope. Call this S sub M, if you'd like, for the motor itself. So the total length of the cable in this case would be S sub M plus 3 times S sub A. When we differentiate once with respect to time, 0 is equal to Vm plus 3Va. We find that the speed of that position M as it's being pulled into the motor itself is equal to negative 3 VA. VA, recognize, is this speed here that we solve for. This is the speed at which the crate is moving towards the left. Okay? So plugging in 1.704 into this equation, we can solve for the speed at which the rope is being pulled into the motor. It's 3 times this value. So if we multiply that value times 3, we find that Vm is equal to 5.111 meters per second. This is the speed that the rope is getting pulled towards the motor. The force at that instant, at 5 seconds, we said was 220 newtons. We solved that long ago. The product of force and speed is going to give you your power. The power turns out to be 1124 Newton meter per second, or joule per second, or big W for our homeboy, Mr. Watt there. And that's how we can solve the problem. I know that it took a longer because I was talking through it, but using the linear impulse momentum equation is actually a little bit faster way to solve this problem than using your equation of motion, which you would need to integrate from your acceleration to your velocity. This is a more direct way to solve the problem itself. The value of learning the linear impulse momentum equation is that we can solve problems very quickly that involve force, velocity, and time. We had force as a function of time. We're trying to solve for power ultimately, but power is related to velocity, and the magnitude of that being speed. So this was a great equation for us to develop so that we could solve this problem so quickly.